Alessio Santamaria with a talk entitled Towards a Calculus of Substitution for Dinatural Transformations.
Thank you. I'm going to try and share my screen and see if I'm successful at all. Can you see my screen?
Yes.
Yes? Okay. So thank you, Eduardo, and thanks also to all the other organizers of this ItaCa Fest for giving me the opportunity to speak here. In this talk, I will tell you a story that starts with a project of Max Kelly back in the 70s, and that my personal PhD project ended up being part of, I belatedly discovered. And therefore, all the work I'm going to present here, which is my PhD, which I defended last year, is as such joint work with my supervisor, Professor Guy McCasker, who was done at the University of Bath. So this story begins with an extraordinary transformation. If you take any Cartesian closed category, we can always consider the evaluation morphism eval AB from every object A and B that goes from A times A plus B to B. This would be the internal home. As a family in B, this is a natural transformation. However, in A, you can notice that the variable A appears twice in the domain, once covariantly and once contravariantly, and never in the codomain. Therefore, this is not quite a natural transformation. However, it still satisfies a sort of a universal equational property, because it is true that for all f from A to A prime, a square like this, which is kind of a naturality condition, commutes. You can see, however, that the transformation appears in this bottom right corner, and the morphism f jumps from the contravariant instance of A to the covariant instance of A. This quite trivially commutes in set. It just means, something very simple, and use the internal language, for example, of any Cartesian closed category, and you can prove the commutativity in an arbitrary Cartesian closed category. So, in 1966, Eilenberg and Kelly noticed this example, and they realized that the usual calculus of functors and natural transformations wasn't quite capturing this phenomenon, which is not that rare, which is not that exotic in nature. And so they introduced a generalized notion of natural transformation, which nowadays we call extranaturals. And here I'm going to show you the original definition. So given two functors f and g, f from A times B op times B into E, and g from A times C op times C to E, an extranatural transformation phi from F to G is a family phi ABC from F of ABB to G of ACC, such that for all f, g, and h, these three squares here commute. Now, if you focus on the top left one, you can see that this is a classical naturality condition on the first variable on A. So this is why we would say that such a phi is natural in A and properly extranatural in B and C. If you look at this one at the top right, you can see that the transformation appears in the top right corner, and the morphism G jumps from the contravariant instance of F in the category B to the covariant instance of F, just like the eval that we saw before. And this is just, the third one is just dual to this one, where you can see that now the H is a morphism of C, which only appears in the functor G and so on. So, of course, the original definition here was with three variables, but you can well imagine this family depending on less than three variables. For example, if one of the categories A, B, and C is the terminal category, here we will have less than three variables. And at the same time, the categories A, B, and C can be themselves products of categories, in which case here we just have more than three variables. So, the original definition can be three, but obviously you can have a notion for an arbitrary number of variables. However, there is one important constraint that is intrinsic in the definition, and that is the fact that every variable of the transformation has to appear exactly twice when we write down the general component of phi. So either once in the domain and once in the codomain like the A's, or twice in the domain and never in the codomain like the B's, or vice versa like the C's. So now, extranatural transformations, as you can see, generalize the ordinary natural ones, but they're not quite as well behaved because, in fact, they don't compose. Indeed, if you take two consecutive extranatural transformations, just like in the definition of phi and psi, we can form the family of morphisms phi ABC followed by psi ACD. But this family is now a family that depends on A, B, C, and D. In particular, it depends on the variable C, which does not appear in either F or H. And therefore, this is not a well-defined extranatural transformation from the functor f to the functor h, because it depends on something that has nothing to do with either f or h in general. And besides, even if we allowed for extranatural transformations to have ghost variables, let's say, variables that are not involved by either the domain or the codomain, for such a family to be extranatural in that ghost variable, it should be constant in that variable. And there are counterexamples to this, so this doesn't happen in general. Compositionality doesn't work in general. However, that said, Alessio and Kelly already in 1966 did find a sufficient and essentially necessary condition on two consecutive extranatural transformations for the composite to be in turn extranatural. And to do so, they associated to each extranatural a graph that somehow reflects the signature, that tells us which variables of the transformation, each of the functors, domain and codomain, have to be equal to each other, which of the arguments of the domain and the codomain have to be equal to each other when we write down the general component. I'm going to show you how to draw such a graph. Actually, the graph I'm going to draw for you is not going to be exactly the same as the one described by Alessio and Kelly in the original paper, but carries the exact same information, so it's equivalent from this point of view. So, for example, take any extranatural, just like in the definition, for example, from f of ABB to g of ACC. Here I'm going to draw bit by bit the graph corresponding to such a phi. So I will start by drawing 3 upper boxes, one per argument of f, the domain of phi. In this case, I drew 3 because f has 3 variables, but if f depending on, say, n variables, then I would draw n boxes. Notice that the f, the brackets, the commas, they're not part of the graph. They're just there to let you understand what is going on. I drew in gray, in particular filled in gray, the variables of f that are contravariant. And I do the same for the codomain. So I draw as many lower boxes as the number of arguments of g. If g depends on m arguments, I would draw m boxes. In gray, those ones corresponding to the contravariant arguments. And then in the middle, I would draw as other kind of vertices, 3 black squares. I drew 3 because in this case, the transformation depends on 3 variables. If the transformation depended on k variables, then I would draw k black boxes in the middle. And then you see, when we write down the general component of phi, so phi ABC, we have to compute the functor f in A in its first argument, and B in second and third. I'm going to reflect this fact in the graph by linking the first upper box to the A black square, and the second and third upper boxes to the B black square, and do the same also for the codomain. As you can see, I also added directions to these links, and here I just used a convention where I said if your link is connecting a white box with one of the black squares in the middle, then the link is going to go downwards, otherwise upwards. So basically the direction of the arrows reflect the covariance or contravariance in that variable. Notice that we have as many connected components as the number of variables by construction. And now, if you allow me to write morphisms in these boxes, and by interpreting some annotated graphs in this way, as a morphism in E obtained by composing the functor f with the morphisms as they're written in the boxes, compose that with an appropriate component of phi, and compose the result with G computed in the morphisms as they're written in the boxes, then we can interpret in an informal manner the extranaturality condition of phi. What do I mean by this? For example, this was the top left commutative square I showed you in the previous slide, the naturality of phi in A. I would depict the commutativity of this square in this informal, this is clearly very informal way, because I would read this annotated graph where I wrote some morphisms in these boxes as f of f11 composed with an appropriate component of phi composed with g of 111, which is just an identity because g is a factor. And so this here will correspond to the lower leg of this square. The upper leg instead will look like this: identity followed by phi followed by g of f11. Now if we get rid of the ones, so that we tidy up the picture a little bit, and we assume that if you see an empty box, then that's an identity, we get that the naturality of phi in its first variable looks intuitively, in a string diagrammatic if you want, way, looks like this, where the f can travel through the wire. And you can see that naturality conditions are characterized by, in fact, a straight line behavior in the corresponding graph. The extranaturality of phi in its second variable, which was the second commutative square, like the eval, now looks like this. F of 1g followed by phi is equal to f of 1g1 followed by phi. And you see how the extranaturality is now depicted in a geometrical way as a U-turn. And the g can jump from one end to the U-turn to the other. And the extranaturality in C is similar, it's just upside down, is the dual. So why am I telling you all this about these graphs? Well, because when we try and compose extranatural transformations, we can also compose their corresponding graphs. Actually, sorry, let me first show you before I talk about that. Let me go back to our evaluation transformation that we saw like this. We can see it as a transformation from a functor f in 3 variables that given x, y, and z returns x times y implies z, whose graph, the graph of eval, though, looks like this, which tells us, okay, when you write down the general component of eval, make sure to compute the functor f in A in its first 2 arguments, and in B in the third, the same argument that the codomain functor, the identity, must be computed in. And now the extranaturality of eval in its first argument, and the naturality of eval in its second argument, in this intuitively, geometrically, now it looks like this, where you can clearly see the f going around, the U-turns, and the g going up and down. This is just intuition, this is common. So I was saying, when we try and compose 2 extranatural transformations, we can compose their graphs in the same way. Imagine that we have an extranatural phi, whose graph is the top half of this graph, and psi from G to H, whose graph is the bottom half of this graph. In order to compute the graph of the composite, all we have to do is to glue together the graphs of phi and psi along the boxes corresponding to the functor that they have in common, the one in the middle. And all we have to do is then, after we do that, is to pull the wires, essentially, and to collapse the entire connected components into one single black square, one per connected component. In this case, there is only one. And we get a final transformation. In this case, this transformation, this composite transformation, would be, in fact, a natural transformation, because intuitively, you can imagine that if you put an F in this top left box, this F can travel through the wires and end up here. This is a straight line behavior. This is a natural transformation. However, things don't go this smoothly every time, because you can imagine that we have instead a transformation phi, like whose graph is this top half, and a transformation psi whose graph is this bottom half. And as you can see here, we end up with 2 connected components, the composite graph. So the composite transformation is going to be a natural transformation in its first argument. But in the second, it's not quite clear what it is, because here we have a cycle. This is one of those cases where we have a transformation, the composite transformation being a transformation in 2 variables, the second one of which being a ghost one, being a variable that is not involved by either f or h. And the theorem that Eilenberg and Kelly proved in 1966 is precisely that if the composite graph of 2 consecutive extranaturals is acyclic, then the composite transformation is indeed extranatural. This condition is also essentially necessary in the sense that if the composite graph of phi and psi contains a cycle, then the composite transformation is not a well-defined definition, in fact. It is not a well-defined extranatural transformation from the composite, from the domain functor of the first to the codomain functor of the second, like we discussed earlier. So this happened in 1966, but 6 years later, Kelly started the project I mentioned at the beginning. It was a project related to, with the final aim to give a proper abstract theory of coherence. And what does this project says? Well, Kelly argues that in general coherence problems are concerned with categories carrying an extra structure. There is a bunch of functors and natural transformations, all subject to various equational principles. For example, if we take the theory for monodal categories, this involves a category C together with a functor tensor from C squared to C, a unit functor from C0 to C. If we have, if we talk about the monodal closed case, then we would also have an internal Hom functor, which is of mixed variance. And then we have natural transformations, for example, the associators or the unitors, symmetries, and so on. Now, if you look at this basic, for example, here, Kelly says that the basic natural transformations connect not the basic functors that come together with the data. but rather functors obtained from them by iterated substitution. So by iterated substitution, we mean the process whereby, given, for example, functors k, f, g, and h like this, where you can see that the codomain of f and the codomain of g and the codomain of h are the categories that form the factors of the domain of k. We can construct a new functor, which is k of f, g, h, which would be the substitution of f and g and h in the variables of k, which acts in the obvious way. The given a, b, c, d, and e returns k of f, a, b, g of c, d, h of e. So this is what Kelly calls about iterated substitution. You can imagine that this being substituted into another functor and so on. And obviously, iterated substitution is just a generalized notion of sequential composition of functors, to which it reduces when all the functors involved are just of one variable. In the same way, Kelly says, the equational axioms that the natural transformations that come, that are part of the data are subject to, for example, the pentagon axiom in a monodal case, involve not the basic natural transformations, but rather natural transformations obtained from them by substituting functors into them and them into functors. So for example, if you look at this transformation here on the top left, this is a family of morphisms in 4 variables, a, b, c, and d, which is obtained by substituting the tensor functor into the first argument, in the first variable of alpha, whereas this transformation here on the bottom left is obtained by substituting the alpha, the natural transformation alpha, into the first argument of the tensor functor. So as you can see, the operation of substitution of functors into transformations and transformations into functors is just a generalized whiskering operation, or even better, a generalized horizontal composition of natural transformations. So Kelly says, if we want to achieve a proper abstract theory of coherence, what we need is a tidy calculus of substitution of functors in many variables and appropriately general natural transformations. Such a calculus ought to generalize the usual calculus of ordinary functors in one variable and ordinary natural transformations. Kelly does manage to achieve such a calculus by using the same idea that he had with Eilenberg in the study of extranatural transformations, because he says, I actually quite like the idea of having the notion of a transformation together with a graph. And why don't we apply this idea also to ordinary natural transformations rather than just those extranaturals with those U-turns? For example, this is an example that Kelly explains. Take any category C with finite products and consider the diagonal transformation. This is typically seen as a natural transformation from the identity functor to this composite functor here, which is the product functor composed with the diagonal functor, the functor that goes from C to C times C. But we can rather see it instead as a natural transformation delta from the identity functor to the product functor, which is a functor in 2 different variables, together with a graph like this that tells us that in order to write down the general component of delta, we have to equate all the variables of the domain with all the variables of the codomain factor. Indeed, delta A goes from A to A times A. And now, so just en passant, I'll show you very briefly the naturality condition of delta, which is the commutativity of this square. Now, from the geometrical point of view, is depicted in this way. You can clearly see the F being duplicated. So, as I said, Kelly managed to achieve such a calculus, such a full substitution calculus, in the covariant case only. And his starting point, I'm going to show you very briefly how he did it. His starting point was the fact that the usual calculus of functors and natural transformations stems from the assertion that the category cat is a true category, that therefore has objects that are categories, morphisms that are functors, and true morphisms which are natural transformations, which vertically and horizontally compose in a coherent way. But Kelly says this is saying less than saying that cat is a Cartesian closed category, because the functor B blank, this is the functor category, has a left adjoint, as we all know, that is blank times B. Now, given that every Cartesian closed category is enriched over itself, where the cat is a cat category, which is just another way to say true category. Now, vertical composition of natural transformations, he observed, is embodied into the internal home. because are the morphisms of this category here. But sequential composition of functors and horizontal composition of natural transformation, that the rest of the usual calculus, are embodied into this functor here, which is given by the Cartesian closed structure. You obtain it from the adjunction by using the evaluation map twice. And so, in order to achieve the substitution calculus that ought to generalize the ordinary calculus, what he did is to define a generalized functor category, curly BC, whose objects are functors in many variables, so are pairs of a natural number and a functor from Bn to C with their arity. And morphisms between two such things are natural transformations in many variables, together with the Allen-Branchelli graph that tells us which variables of f and f prime have to be equal to which among A1, AK, when we write down the domain and the codomain of phi A1, AK. And he defined an appropriate category of graphs P, whose objects are natural numbers and whose morphisms are Allen-Branchelli graphs in a certain way I'm not going to describe. Essentially, what they are, the objects are natural numbers, and morphisms really are co-spanning things. Imagine them as just Allen-Branchelli graphs that just connect together. And you can see that by just simply forgetting the functors and the natural transformations, this category curly BC is a category over P. There is a functor, a forgetful functor. And therefore, the category curly BC is an object of cut over P. What he proved is that he replaced cut with cut over P. He proved that cut over P is monodal closed, where the curly brackets functor is the internal home. And he proved that, in fact, the functor curly B blank has a left adjoint, which he calls blank ring B.
May I ask you a question, Alessio?
Yes.
Just curiosity. Doesn't take care this of contravariance?
No, not yet. Okay. So he does this calculus only in the
covariant case. So all the variables are covariant.
Exactly. Exactly. So now the calculus of substitution.
I have another question.
Yes.
This circle symbol has nothing to do with a composition.
Yes and no. It's just a notation that he uses. This is notation, so I'm using his notation as well. No, he decides to call it ring for some reason. And now the calculus of substitution that he builds is now provided by the analogous of the functor M up here, which is going to be provided by the monodal closed structure and goes from curly BC ring curly AB to curly AC. And I would like to show you briefly what it is, this category here of this ring of curly BC and curly AB. So I call it the category of formal substitutions, and I'm going to explain you why. The objects of these categories are generated by things like this. An object of curly BC together with a bunch of objects of curly AB. How many? Well, that depends on f. If f is a functor in n variables, then together with f, we go with, we equip f with a bunch of n functors of arbitrary arity from AMI to B. And morphisms are generated by two kinds of generators. One is of the form morphism of curly BC together with a bunch of objects of curly AB. How many? Well, if phi is a transformation in k variables, then we write k factors in all possible ways. And the other generator is of the form object of curly BC together with a bunch of morphisms of curly AB. How many? That depends on the arity of f. These morphisms, and they're subject to some coherence equations, which I'm not going to show, but we can see them as formal substitutions of functors into functors, of functors into natural transformations, and natural transformations into functors. I'm saying formal because all we're doing at this level is just, just juxtaposing an object with a bunch of objects, morphisms with a bunch of objects, and so on. What this functor here does is to take such a formal substitution and realize it as an actual functor with a certain arity from a certain product of copies of A to C. And this corresponds to the operation I described here. When I said the functor K of FGH, this would be the result of applying that m curly m functor to k of square brackets fgh, in a sense. So as I said, he managed to do this in the fully covariant case, and then he tried the mixed variance case, and he started by using the Eilenberg-Kelly extranatural transformations, every variable twice extranatural transformations, but he ran into problems, mainly connected to the fact that extranaturals don't compose, and so it's a bit difficult to define a generalized functor categories whose morphisms are extranaturals because they don't compose. And moreover, there is the problem that, you know, we have a notion of graph, but these graphs can form cycles, and he didn't quite know how to define a category P that could handle these loops floating around. And this is where Guy and I step in, because we realized that the most general case that he really wanted to discuss, that is, you know, the version of this. Can you see me and can you hear me? Yes, okay. That the generalized version of this calculus for functors of mixed variance and therefore generalized natural transformations is really embodied by the notion of dinatural transformation, which was actually already invented in 1970, discovered in 1970. And this is the original definition, I remind you. Given two functors f and g from b op times b into c, the natural transformation phi from f to g is a family phi a from f of a to g of a, such that for all f from a to b, this hexagon here commutes, where you can see the arbitrary morphism f jumps from the contravariant argument of the domain, well, is involved in the contravariant argument of the domain and covariant argument of the codomain in the upper leg, and vice versa in the lower leg. Now, the natural transformations, unfortunately, are mostly famous for what they fail to do, really, and that is the fact that they too don't compose. Because indeed, if you notice, the natural transformations generalize both natural, in the case where f and g are constant in the first variable, and also the extranatural transformations of Eilenberg-Kelly, in the case where one of the two functors is constant. And well, the naturals, like extranaturals, don't compose, but even for a more striking reason. And the fact is that if you take, for example, two consecutive naturals, you can form the family phi a followed by psi a. But the naturality of phi m psi in general does not imply, that means the commutativity of the two inner hexagons, the red and the blue, the commutativity of these two hexagons does not imply the commutativity of the outer hexagon, which means that in general, two natural transformations, consecutive naturals, don't compose to give a natural transformation return. Now, there are some conditions under which this composite does work. For example, if one of the two transformations is natural, this works. If this inner hexagon, if this inner diamond here is either a push out or a pull back, then everything inside commutes. But these are not really satisfactory conditions because they don't really depend on phi m psi. They rather depend on, like, for example, they're either too restrictive or they depend on properties linked to G and the category we're in. And over the decades, people have found several subclasses of the natural transformations that do happen to compose. But a general theory of the natural transformations until recently was missing. So you can imagine that when we realized that what Kelly really wanted to have in the most general case was a calculus of substitution for the natural transformations, which we don't even know when they compose, it wasn't like a very good thing. So one of the main results we managed to achieve during my PhD was precisely to give a solution to this problem, because what we did, we considered exactly like what Kelly would have done, functors of mixed variance of arbitrary arity. So here I write f from b alpha to c, where alpha is a list of pluses and minuses, b alpha is just a product of copies of b and b op. And we take transformations in many variables between them, together with the Eilenberg-Kelly graph that tells us, you know, how to write down the general component of phi. And we managed to prove this, this theorem here, which says if the composition of the graphs of phi and psi is acyclic, then the composite transformation is again dinatural. This, as you can see, is the statement is basically exactly the same as the one that Eilenberg-Kelly gave for their extranatural transformations. However, the proof, their original proof could not be used simply because in their original proof they use the fact that every variable has to appear exactly twice in the domain and codomain of extranatural transformations, which from a graphical geometrical point of view meant that there are no ramifications in the graphs. Whereas here we do allow ramifications, and therefore we couldn't use their proof. I don't have the time to go through the proof. I want to talk about other things. I'm just going to mention the fact that the way we proved it was to interpret the composite graph as a Petri net, and to cast the compositionality property of the composite transformation into a reachability property of the composite graph as a Petri net. If you don't know what Petri nets are, don't worry, because I'm not going to say anything more about this. I'm just going to mention that they are mathematical objects used in theoretical computer science to model concurrency systems. One thing I would like to specify, though, is that this theorem was actually originally already proved by Zoran Petric in the paper G Dinaturality, Annals of Pure and Applied Logic in 2003. And therefore, ours is just an independent rediscovery. We were completely unaware of this result. And so were all the people we talked to for a few years. But Petric actually proved, he too considered generalized the natural transformations like this. He too assigned to each such a dinatural a graph, his graph being a bit different from ours, but still carrying the sort of same information. And he too proved this theorem here. The way he proved it is different from ours in the sense that he went syntactic. He used rewriting rules to prove that the composite is dinatural when the composite graph is acyclic, whereas we went semantic using Petri nets and things like this. I should also say that this theorem here is written as a sufficient condition, but is also essentially necessary in the sense that if the composite graph of phi psi does contain a cycle, then you can prove that, and we proved it, that the composite transformation may be dinatural, but if it is, then the naturality of the composite cannot be inferred from the dinaturality of phi psi alone. Something else must be going on. For example, a certain square is a push-out or a pullback, things that does not depend on phi psi alone. So now that we have vertical composition of the natural transformations kind of sorted, or at least we know when they compose, how about, we know, as I said, this substitution calculus should generalize, the idea of substitution should generalize, or at least in Kelly's case did, the notion of horizontal composition of natural transformations. So how about horizontal composition of dinatural transformations? Well, we looked it up and we didn't find it. And so what we did was we came up with a definition of horizontal composition. But you know, if you do know a notion of horizontal composition of dinatural transformation, let me know, because I might be wrong and this might be yet another independent rediscovery. So I'm going to show you the definition we gave. And of course, given that the naturals generalize natural transformations, obviously the definition of horizontal composition of the naturals will have to be a generalized version of the one already known for natural transformations. And so we got inspired by it. And let me briefly remind you the classical definition. So given two classical natural transformations, phi psi like this, if you remember, the horizontal composition is a transformations that goes from HF to KG, sequential composition of factors, will be generalized with substitution of factors, is a natural transformation from HF to KG, whose eighth component for A in C is either leg of this commutative square. The reason for which this square is commutative is because psi is a natural transformation. And then it turns out that this family homomorphism so defined is in turn a natural transformation indeed. This operation is associative and also unitary, and satisfies an interchange law with vertical composition. But if you look at it, in order just to define the family of morphisms, all we did was to write down the naturality square of psi that holds for any f from A to B, and instead of the general f from A to B, we instantiated it with the general component of phi. And then we did that for all A, and we built up a new family. And so how about doing the exact same thing with dinaturals? So consider two classical dinatural transformations, phi and psi like this. Then we define a new family of morphisms, for the moment just a family, psi star phi, that goes from H of GF, this is the substitution, the iterative substitution Kelly was talking about, generalized composition of factors, to K of FG, whose general component for A in C is given by either leg of the dinaturality hexagon of psi instantiated on morphism phi A for every. And so in doing so, we obtain a family of morphisms. That's all very good. But is this a dinatural transformation in turn? And the answer is yes. As it happens for the natural case, where you use the naturality of both phi and psi to prove the naturality of the horizontal composition, so happens here with dinaturals, saying this is the proof. The outer hexagon is the naturality condition of psi star phi, and you can see that this can be filled with a trellis, with a honeycomb, I've been told, of commutative diagrams where we use the naturality of both phi and psi twice, in fact. So notice also this curious phenomenon where this operation of horizontal composition is better behaved than vertical composition because there are no hypotheses on phi and psi. So given two arbitrary dinaturals, the horizontal composition is always dinatural. It also turns out that this operation is associative. It is unitary, again, the units being an appropriate identity functor, identity transformation over an identity functor. And how about compatibility with vertical composition? Well, what happens in the natural case? Compatibility in the natural case look like this. It just said that if you have four natural transformations like this, you can either perform the two vertical compositions first and then horizontally compose the result, or you can also perform instead the two horizontal compositions and then vertically compose the result, and the two things you come up with are the same. And does a law like this hold for dinaturals too? And the answer is no. The answer is no, because if we take four dinaturals like this and assume that phi psi and phi prime psi prime do compose for some reason, then, and we try and compute their horizontal compositions of phi prime with phi, like we did here, and psi prime with psi, you can see that the codomain of the first transformation is not equal to the domain of the second. Because f is not equal to h in general, and there is no way to go from f to h in the contravariant argument of k. So there is no way to just link these two, and this means that there is no such an interchange law. At least there is not an interchange law that looks like the naturality, the natural one, the one from natural transformations. What we suspect, we haven't found an interchange law yet. What we suspect is that a different interchange law exists. It's just going to be an interchange law that doesn't have this shape, but something that somehow accommodates the more hexagonal shape of the naturality rather than the square shape of naturality. But this is just ranting at this point. We just don't know an interchange law yet. So this is an open problem. It's one of the reasons for which this is like one of the complications we have. But anyway, now that we have an operation of vertical and horizontal composition, what we did was we started following Kelly's steps, the steps that he did in the covariant case for the mixed variance case this time. And the first thing we did was to define a generalized functor category. So this is the using, of course, the compositionality theorem that we came up with. So notice this generalized functor category is not going to have the natural transformations as morphisms because they don't compose. It's going to have transformations that are dinatural only in some of their variables. And so the actual definition is much longer than the one I'm going to give here, but I don't have space now or time. So here I'm just going to give you a sketch of the definition. And the category curly BC is going to consist of the following data. So objects are what we expect, functors of many variables of mixed variance, arbitrary additive. Morphisms now are a bit more complicated. There are triples of a phi, a g, and a delta. So phi is a transformation. So it's just a family of morphisms in an arbitrary number of variables. Delta is a function from the set 1n, where n is the number of variables, to 0, 1, is what I call the discriminant function that tells us in which variables phi is going to be dinatural. This is why I said morphisms are transformations that are dinatural only in some of the variables, not all of them, because otherwise they wouldn't compose. And G is a graph, and it's a bit complicated because it can be either the Euler and Kelly graph of phi, the one with the upper lower boxes and the black mid squares as I described at the beginning, or it can be a composite of Euler and Kelly graph of consecutive transformations phi 1, phi k, in which case phi must be phi k composed with phi 1. This means in particular that the same transformations, the same composite of transformations can appear in many ways as a morphism in this category here. So it's a bit complicated, but all this is made so that composition works. And composition in this category is defined component-wise. So if you have two triples like this, the composite transformation is just going to be the composite transformation. Where this composite transformation is going to be dinatural is going to be decided by the composite delta, which is defined using the compositionality result. And the composite graph is just going to be the one obtained by gluing the graphs together and carrying everything around. Now, these lists and these graphs defined in this way can be themselves, organized in a category of graphs, which intuitively is just a category that is obtained by forgetting the functors and transformations from curly BC. Obviously, this is not a formal definition.
Sorry, Alessio, one question. Since the definition is very convoluted, if I replace B with B op, do I get the same object?
If you replace who? Would
B
yes.
with B op.
Yes.
So
yes.
it is the same, yes.
Yes.
And
because
if
I have B op to the alpha.
Yes,
no.
And if I choose C to be set, I would get something like a kind of generalized Presheaf category. Did you think about it? Does it have some meaning?
Yes, where it's a sort of a dependent, because like the thing is the objects are functors of arbitrary arity and not fixed one. So in this sense would be a sort of a generalized Presheaf category where the objects are not, they don't just go from B op to set, but go from B for an arbitrary product of copies of B, possibly all different from each other, to set. And so we can, just like Kelly did, we can organize a category of graphs whose objects are lists of pluses and minuses and whose morphisms are intuitively chains of Eilenberg and Kelly graphs of some transformations. One can define G independently from BC, and this is what we did. But for this, use this as an intuition. And like Kelly did in the covariant case, we managed to prove that if B is any category, then the functor curly B blank has a left adjoint, which we also called blank ring B. And in fact, the ring functor that goes from cat over G times cat into cat is a functor. And this is the last result. This is the furthest we managed to get in following Kelly's steps. So I'm just going to conclude with what is left to do to achieve such a calculus. So the substitution calculus for the mixed variance case is going to be yielded just like what happened we expect is going to be yielded by a functor curly M that goes from curly BC ring curly AB to curly AC, which what it does is computing a horizontal composition of the natural, because again, a morphism here is again going to be a morphism of BC together with a bunch of objects of AB, or an object of BC together with a bunch of morphisms of AB subject to some equations. So all you have at the end basically is a sort of a formal substitution of a dinatural transformations into another. And so we expect that such a functor, what it will do will be to compute the horizontal composition, given a formal substitution of a dinatural into another. The result of it will be the horizontal composition of them. And this functor, which we don't have yet, will arise from an adjunction like this, exactly like in Kelly and Kelly case. But we don't have this adjunction yet, because in order to have that, we will have to extend this functor ring that at the moment just goes from cat over G times cat into cat, to a functor that goes from cat over G times cat over G to cat over G, which means essentially that we will have to find a way, given two categories over G, to embody, to equip A ring B with a structure of a category over G, so a functor towards G. And to do so, what we need to do is to find a way to define a functor that goes from G ring G into G. The given a formal substitution of graph into another computes a graph. Because if we do to manage a thing like this, then given a dinatural transformation here and a dinatural transformation there, the graph of the composite dinatural transformation, which is the graph of the horizontal composition, will be the one computed by this functor here. So this is where we are stuck in. We are trying to find a way to define a notion of substitution of a graph into another. We have some intuitions on how to do it, but no formalizations yet. And so this is where, this is the state of the art, essentially. This is part of my personal project. And so with this I conclude. You can find all the details in this preprint we submitted. You can find on archive. And I thank you very much for your listening.
Thanks for the very nice talk, Alessio. And are there any questions?
Have you tried to link this generalized substitution calculus with the Kelly notions of club and
Yes.
the operatic characterization of clubs?
So the reason the clubs are strictly related with this, because clubs are monoids for this ring functor.
Yes.
Well, at least in the fully covariant case where we had this functor. So as yet, I haven't. In the mixed variance case, I haven't, just because we still don't have, the proper signature. We haven't extended this functor ring to what we ought to do, which is to extend it to a functor cat over g times cat over g to cat over g. Yes. But if we will manage one day, hopefully, then the next step after doing all this is to study the notion of club for the mixed variance case, which Kelly did manage to, he did manage to define a notion of a club for the mixed variance case for the extranatural transformations, at least when we were in where loops would never arise upon composing the graphs of certain transformations, which were the real problem, those loops, really. So no, we haven't done it yet because we don't have the right structure yet.
Of course.
But it's definitely like at the horizon.
So you expect that there is an analog even changing P with G? That was
yes, exactly. I would hope so, because I mean this G aims to be a generalized version of P.
Indeed, yes.
So I will hope that we are not generalizing so much to lose like the calculus of clubs and I think.
Yeah.
But we'll see.
Interesting. Thank you.
Thank you.
Other questions?
I have a quick question. So a lot of this approach seems quite axiomatic, and I was wondering whether it might be generalizable to a setting where you have something like a 2-category with a duality involution. So you start with some 2 cells which represent the natural transformations, and you try to come up with some mixed varianced version of transformation in a non-cat setting. Do you think that's something that might be possible, and have you thought about it at all?
I haven't thought about it, but it will be possible because, I mean, one can prove the cat over G, in fact, is a sort of a, well, at least in the covariant case, it was like a 2-category, and this would be a 2 functor and so on. So I imagine it might be possible, but the mixed variance is a great complication on top of the fully covariant. So I'm not sure. I haven't thought about it. I don't know.
How do you generalize the naturality or extranaturality to an abstract 2-category? Because I have thought about this for a little while and I haven't come up with.
Then I really don't know. No, I haven't thought about it. So yeah. It's clearly not trivial, surely.
And in the same direction, maybe the 2-category will not have enough internal logic to create an instance of P or G.
Probably you can, you remember, we tried to define analog of a certain kind of extension that defines coherence in a Yoneda structure. But you need the Yoneda structure to be quite expressive to say that. And in fact, the existence of such universal objects, let's say, as abstract objects of a 2-category with a Yoneda structure are very tightly depending on the Yoneda structure axioms. So at least, I think, yes, you need a very expressive two category to cast denaturality. You see why I'm calling coherence into play, because
yes,
they are, yeah. But denaturality seems quite elusive.
It is quite elusive, yes. It's not very well behaved, apart from the fact that horizontal composition works
Of course, yeah.
really well, apart from, well, not really that well, because it doesn't really compose, doesn't really behave well with vertical composition, but also vertical composition doesn't behave well. So, and that's the thing, that like, if we do manage to find such a functor, the interchange law we're looking for is probably written here.
In the functoriality.
In the functoriality condition of this n.
Of course.
But maybe we won't find a functor. Maybe we'll find a sort of a pseudo functor. I mean, not pseudo functor, but like
yes.
You know, weak functor of some sorts.
Yes.
And maybe it's hidden there. So we just hope, but we'll see.
And what about some more algebraic properties of the horizontal composition of denaturals? Have you thought about the special case where one of the denaturals is constant, so that you can say something about maps induced from ending and co-ending the other?
Yes, well, ends and coends are particular cases. Yeah. I did think of, honestly, here from the top of my mind, I can't remember, but I do remember going through like what happens with ends. We use ends.
Can you go back to the slide where you described the horizontal composition?
Yes. This.
Yes, because if, let's say,
you want
if you assume F or G, if you assume F or G to be constant, or H or K to be constant respectively, then you will get some suitable induced maps from or to the end or co-end of the functor you are considering. And probably these tell you something about an algebraic compatibility. I would call it an algebraic property of horizontal composition with respect to co-ending. Probably it's useless, but if you want to know something more and you haven't thought about this.
No, I haven't thought about it, but yes, I'll note it down.
Thank you.
Thank you.
Are there other questions for Alessio?
I have a question, I think. Hi, Alessio. No, just, I don't know if I understood all the things, because it's quite involved with everything. And but this is my question. When you compose horizontally composed natural transformation, you can reduce the composition of a natural transformation in a vertical composition by using whiskerings, you know?
Yes.
Yes. I was wondering if something similar happened in this respect to this.
The most general. Yeah, sorry, continue.
Yes, and if maybe the interchange rule is the sort of of mirror of this behavior.
So perhaps surprisingly, so here I define the notion of horizontal composition for classical dinaturals, but one can define it also for generalized dinaturals in the sense I described before, where the functors f and g don't necessarily go from the same copy of products of C, and they might have like different arity and so on. And in the most general case, and psi can be transformations in many variables, in the general case, the horizontal composition is not a vertical composition of whiskering, whereby whiskering would be the special case where either phi or psi is an identity factor, is an identity transformation over a factor. No, because, well, in the one variable case, yes, it is. But in the many variable case, it's not. It's very weird what goes on. because the reason for which I'm saying this is that suppose that phi doesn't depend on one variable, but depends on k variables, say. When you compose, and psi is like this. When you compose psi with phi horizontally, what we have to do is to write down the hexagonal, the naturality hexagon of psi and instantiate it on the general component of phi, which will be phi A1AK. So that means that you put the same component of phi here and also here. When you start, when you do the whiskerings and you try to vertically compose them one after the other, you end up with situations in which the variables you use here and the variables you use there are not necessarily the same. I don't have it written here, but it's a weird phenomenon we noticed, which means that like horizontal composition so defined is not, although you can define a whiskering operation out of it, it's not a vertical composition of whiskerings, not always. It's a bit bizarre, but at the same time, this definition works. So it might well be that maybe there is another definition of horizontal composition, obviously. But this one really works. Like, first of all, it uses the exact same idea behind the definition of natural transformations, which is a very natural idea. And it's well defined, it's associative and unitary. So I think it's unlikely there is another one that behaves better than this one, really. It would be asking too much in your opinion, but maybe there is. I don't know.
Because no, well, okay, maybe we discuss later on.
May I ask a question?
Yes, please, Pino.
I would like to understand if your final comment on the ring on G is the necessary tool that you need in order to achieve what you want, or because you stated it in a very informal way. There could be other ways of mixing cats over G with other cats over G to obtain a cat over G, or is it necessary to have such an S?
I think it is, in the sense that, so this operation ring must work. So G is an object of cat over G. So we will have to define a factor like this. Well, a factor. We will have to define, we will have to expose G over G, G ring G as an object here anyway. And due to this fact, I think that it is necessary to, because then you define, if you define it like this, then you can define it for an arbitrary category over G, but just building up like but just factoring through this S, essentially. And at the same time, you have to define such an S anyway in order to have this. So I think it is necessary. Once upon a time, I was much more into this stuff, so I would have been able to reply much more quickly. But I think yes, I think it is necessary.
Okay, thank you.
Okay, so if there are no more questions, I would like to thank again both speakers on behalf of the ItaCa program committee. I've also posted on the chat the Facebook group, which you can join, and Fosco and Ivan posted the Fosco posted the page for the ItaCa project, so you can check both links. And so now we can, whoever wants to stay, we can stay here for chat, and then, as I said earlier, depending on the numbers, we will decide how to organize this. But you're more than welcome to remain for chatting with all the others. And also, of course, thanks for having joined us for this event.